Image classification using Landsat 7 Thematic Mapper, or TM. Landsat 7 Thematic Mapper has been the principal instrument that we've used for land cover classification for the last 30 years or so. It really produces very robust data, relatively high resolution, high to medium resolution, I guess you'd call it, 30 meters, but a really useful tool with the 6 multispectral channels and then the thermal channel as well. But we mostly use the 6 multispectral channels, 1 through 5, and channel 7. They give us a nice spread across the visible and near and mid infrared spectrum. And so here's the problem. We have 48 bits of data, 6 bytes, 8 bits per channel on the 6, 1 through 5, and 7, channel 7. And so we typically do work with those 6 channels, and then that gives us 2 to the 48 possible values, 48 bits, 2 to the 48th power possible values in each pixel with 6 8-bit channels. That'll give us 281 trillion possible values in each pixel. This is a real problem of data. Just massive data that we really have to make some sense of. So here's where our TM channels are. We have channel 1, 2, and 3. These are the visible channels, and then 4 near infrared, 5, and 7 in the mid-infrared, channels 5 and 7. And we're really looking at averages that really are approximations of the area under the channel. So you can see there's even variation within the width of this band. So this is a relatively coarse measure for for resolving the spectrum. So the purposes here are well stated, I think. We want to bring it down from 281 trillion down to a number a little more reasonable, like something under 20, probably 20 different classes is about as high as we go. Sometimes a little over 20, but typically that's about the normal number of classes that we have. So there's other purposes that are obvious, I think, when you start doing this. Hard and soft classification. Hard classifiers make firm decisions. Soft classifiers make less firm, where there's more variability and possibility of flexibility within classification decisions. And we also have either unsupervised or supervised classification. And what we've done in our lab activity just through the years has been supervised classification. This is where, this is really the strongest type of classification, where the analyst knows some things about the area that they're classifying, and they create a classification. I think that's a stronger classification, more useful classification, because we go in with known information and we target particular types of land cover that we're interested in classifying. So the basic steps involve the training stage, where you set up training sites, and you do this by digitizing polygons around areas that are coherent, that show the types of land cover that we want to classify. You use that to produce a signature file, and then you go into the classification stage, part 2 in this diagram. And then ultimately you do produce output. Output, is a classified image where you have very simple land cover classes, or usually a very simple system of land cover classes that are assigned to pixels that we at one time had 281 trillion possible values there. Now we've reduced it to a much smaller number. So this is a diagram that just shows you a little bit about how in 2-channel space here, channel 3 and channel 4, how in 2-channel space particular training samples of different types of land cover, mostly agricultural and urban and water land cover classes, how these might plot in a scatter plot in two-dimensional space. Now you have to remember we're working in six-dimensional space in this activity, so this graphic really only displays two of the channels at one time. So the different methods that we learned some things about, I guess, and we're going to try out one of them. The different methods include minimum distance to means, and here you have an unknown pixel at this position 1 on these two channels that we're trying to classify. Here it's going to be classified as corn because that's the minimum distance to the mean for that particular pixel. Parallelepiped classification scheme that uses really the minimum and maximum in each of the 6 channels to make determinations about where a particular pixel will be classified. And then equal probability contours of a maximum likelihood classifier. I think this is what we used in our activity too, and it's a very strong classifier that really estimates a surface that you can see the contours of for each of the training samples, and then takes an unknown pixel and rates it on all of the different classifiers and selects the classifier that has the maximum likelihood for that pixel being a member of that particular class. So here's just an example of how when you start out with Cook County, here's 24 bits of data, or 16.7 million possible colors in Cook County, but with the actual data that we have, again, it can go much higher than that, the possible values that we have. Now we've classified that, we've reduced the number of values here to 14 from 16.7 million, so this is much simplified, much more generalized, and we would think much more useful for our decision makers to use in making decisions about land use planning.